I guess we're ready to start. Welcome to this performance evaluation course. The course is being recorded for those of you who want to see the lectures offline if you want. This is why we have those beacons around. Don't worry, this is not recording you, it's just recording the stage here. The team, I'm your lecturer, Jean-Yves Le Professor downstairs in the Lab for Communication Systems. And our TAs are Eleni Stein, who will also be replacing me for 1 week. The third week I will be on trip, and Eleni will give the lecture. And the TA who will also help you with the exercise is Ehsan. Where is Ehsan? Who just disappeared and was around a minute ago and will be back. Here is Ehsan, the hero of the day. And Song is helping for the camera. Song is finishing his PhD and is not TAing this semester. Everything is on Moodle. This is also for some long-term material, but you go to Moodle and you will find all the material, including the slides, the recordings of the videos, the homeworks, and we'll talk about that in a minute. We will use SpeakUp, which is a little tool that you can find online to help interaction in class. We're a small class, so in principle, perhaps we should not need that. But the benefit of SpeakUp is that it is anonymous, so don't be afraid of giving the wrong answer. It is by giving the wrong answer that you learn. By giving it once, then you know the second time, in principle, and that's much more efficient than always being right. So if you go to SpeakUp, if you're lucky, you will see the class because we're close to it. If you're not lucky, depending on your device, you will need to give a room number. This is the room number for today. And once you have found the room number, once in a while, when I am asking a quiz, I post a multiple choice questionnaire. And then you should see on your device all the a screen that invites you to give the possible answers, which we can try now on this question, which will also help me understand your background and why you are here for. I see that not many of you did answer. We have 10 votes, and you should see also the histogram on your screen of the distribution, which is master student in CS, master student in some other program, and PhD student. Here is how this course is structured. We have 2 hours of lectures every Tuesday and 1 hour this is not Thursday, this is Wednesday. The time has changed between the time I did the slides and the final allocation of slots. So this is Wednesday, tomorrow, same place, same time. We will do a lecture for covering the theory, and after that, today at 3 o'clock, we will do what I call a pencil and paper exercise, which is a set of questions that are posted already on Moodle. You can find the set of questions, and we'll go through them here in class, and you will go through them, and I and the TAs will be in the room to help you with your questions. And later tomorrow, we will post the official solutions so that you can compare your solutions, and you have until tomorrow to try yourself at this. That's the theory part of the course. This course is about applying probabilities to do real world stuff, experimental stuff. So we will not do chapters in probability. A requirement of this course is that you know a bit of probability, not the advanced one, but fundamentals. We will go through what they really mean and how we can use them to do performance evaluation. So there is some theory to it. Of course, there's a large part of practice, but there is some theory, and the theory we will test it and experiment it through these pencil and paper and pencil exercises. On the second day, on Wednesday, there will be 1 hour of lecture. So tomorrow there will be 1 hour of lecture. Every other week there will be a test, a written test, which will be similar to the pencil and paper exercise we do. Just a way to make sure that by having constant Dirac peaks of activity every 2 weeks, that it's more or less constant over the semester. Right? Experience has shown that this dramatically improves the understanding of the lecture and the performance of everybody. Then after that, when there is a test, the test will be before the lecture. Otherwise, the rest of the second day is self-paced homework. The homeworks are 4 practical programming exercises using a tool for numerical programming. There are many. This lab has been designed using MATLAB. The 4 labs have been designed using MATLAB. If you use MATLAB, that's fine. We'll be using the same language and it can help you very efficiently. We also know Python, and we can use also NumPy or other Python packages to do the same thing. You can also use Julia or even C++ or Java to do. It's relatively irrelevant which language you use. You just need to have a language in which it's easy to do things like plotting and mathematical evaluations. It's possible in practically every language. There are some languages like MATLAB and NumPy where it was made for that, so the learning curve is very small. The labs will be on 4 topics. The one that we'll cover today is what we call the scientific method. We'll talk about that a bit later. Then about simulation and statistics, a bit of queuing theory, and a bit of forecasting. So as I mentioned, there will be tests. The course is structured in 2 parts. So the practical part will be in the second part of this course will be your own lab, what I call a mini project, which is the size of 2 labs. So the last 4 weeks, there will be no lab. Instead, you will do your own lab, which is a performance evaluation study that you will do on your own topic. Since we're a small class, we can afford that. And after all, that's the goal of this course, is that you can use this not to become a performance evaluation expert, but to correctly do the performance evaluation of a project that you're interested in. We'll talk more about this in a few minutes. Are there any questions so far? If there are, don't hesitate to ask. The grading. So there is the written exam in the exam session, so in June, I guess. The tests, we take the average of the best 4. That means you can skip 1. If for whatever reason you're sick or you have an emergency, programming, advanced programming lab, programming marathon with 4 nights and you can't do it. So whatever the reason, that means also if you're sick for 1 week, we don't have a makeup for that, except if there's a really dramatic situation, we can always discuss it. In principle, we erase 1 of the 5 tests. The homeworks, we take the average of the 4, and the mini project counts also as much as all the homeworks, and we take the average of all that. The written exam will be without document, because it's very hard for us to control what really who gets what. So there is what I call an exam booklet, which is a series of formulas, which is already on Moodle, so you can see what you will have available at the exam. So whenever you progress through the course, if you wonder, should I know this formula by heart, then you can see whether the formula is in the booklet. In principle, everything that looks like a formula is in the booklet. So you don't ask that you know formulas by heart, but that still you know a number of things so that you don't discover them the day of the exam. The lecture notes are this book here, which you can buy if you want. Otherwise, it's also freely and legally available at this site, or also, yes, I guess on this site here. So it's legal because if you have press allowed it after they sold it in 1 year, and after 1 year, that's a deal they accepted, they make it free. In fact, if you go online here, you will even have the version with the bugs corrected. At least the known bugs are corrected. That's the outline of the lecture. I'll come back to that a bit later. A few words about the mini project. That's something you have to think already now. So the goal is, as said, to work on your own project. So that means you have to do some inspection, and by a date, that will be explained a bit later, I will ask you to define in one paragraph what this project will be. Then I will talk with you to see if this is okay. So we will take 1 or 2 weeks to refine the topic well before it starts. So what you have to imagine between now and 6 to 8 weeks from now is what this mini project will be. It can be whatever you want, and here is examples of past projects. As you see, there's quite a large number. Some of them have to do with comparing the performance of programming language, of some communication protocol, this or that, of various distributed systems, of I think there was a cartography web application, etc. So it can be any project that you are interested in. It can be a project that you did in the past semester, or even that you're doing this semester, or your pet project on which you work during your free time, whatever. So the procedure will be that you have to define in one paragraph what it is, and the goal of the mini project is not to invent a new programming language, for example, and then compare its performance. It's to analyze the performance of something that you already have. Right? The goal of the project is not to refine whatever other project you have. It's only the size of 2 homeworks. So 4 weeks of homework time. It's a small thing, but the good news is that this is, when we have learned this stuff in the course, we can do it in that short amount of time. So by this deadline, April 3rd, which is in 6 weeks from now, do this one paragraph that I mentioned. And then by April 10, this should be finalized with me. I mean, you should receive the green light from me by Moodle saying it's okay, or I will talk to you either by Moodle or in class here at the break if I don't understand something, or what very often happens is that the thing is too big. So you want to do performance of C++ versus Java, okay, but this will be a PhD thesis, not a mini project, so you have to be usually more specific. Also, you have to address a problem that is not obvious. Right? Is it faster to go by car than by bicycle to Zurich? Yes. So you don't need to do an extensive study by sending 10 people by car and by bike and see how much time more they take, etc. So if the answer is obvious, don't do it. Right? Don't do a performance evaluation. It's only if there is something to learn in the answer, either by quantifying the benefit or when it's not clear what the outcome will be. That's the topic of the goal. What's the goal of a performance evaluation? Very often we don't need it. And we will see, in fact, techniques that avoid doing performance evaluation in a few minutes. So once this is done, during the last 4 weeks, you will do it. So this will replace the lab session. We'll also provide support for you as much as we can. Typically can't provide a lot of support for the project-specific thing. If you're doing an imaging project on how to reconstruct 3D moving images, then we don't have expertise in that. But we can provide expertise in the performance evaluation of that. And in the last week of the course, last 2 weeks, in fact, there will be in this room public defenses where each of you presents the work, and part of the work of the performance evaluation work is how to present the results. That's a very often disregarded part, but we will also monitor that. And to make sure this happens well, you will do a dry run of an interim presentation, not in the class, but just with me and perhaps one TA before, to make sure that everything is correctly in place. So we'll also work on the soft skill on how to present something that is typically boring, which is result of performance evaluation. It can be 20 slides with curves that go up and down. That's boring, so don't do that, and we'll discuss that privately and also in the course. Here is the complete spreadsheet of the lab. We are here, so today, that's the end of the introduction, and we'll move to methodology. Tomorrow, and we'll do an exercise in the last hour. tomorrow there will be 1 hour of lecture and the homework 1 will continue. Any questions? Anything unclear? Yes?
So we have lectures on Wednesday.
Yes. There is 1 hour of lecture every Wednesday, 3 hours of lecture per week. And during the lecture, as you will see, I interrupt the lecture to do a little quiz. Because you have a problem attending on Wednesday?
I have another class at the same time.
Yeah, but that's why it's recorded. Every year we have the same problem. It's impossible at TCP in the master's program to guarantee no conflict between all the classes. That's why we record them.
So we can access it like a few days after?
Yeah, it will be online there at the end of the day where it's recorded.
And could we consider moving the test to today?
So you have a problem with the test as well. So could we move the test to the Tuesday instead of Wednesday?
Yes.
Why not? Is there any side effect? The last test is here. That means it would be there. Yes, there's no problem for me. But you're not alone. So let us speak up to see if this can be done. Because you have another lecture on Wednesday that is not recorded and that you can't skip.
But if people have lectures now, they cannot be here.
Pardon me?
People have lectures now, complete now, they cannot be here to speak after.
It's true, but that's the bootstrap problem, right? If you miss the bootstrap.
You can send a mail that we solve.
Yes, we can also do that. That's a good point. But let's test the people here. Close this poll. So if 2 answers will say no. Can one of them speak up? Literally. Yes?
I just have 3 hours of class before a little break, so just give us.
That would be inconvenient, but not impossible. Any other? So the other person who said no? Well, if you don't speak up, I don't have any argument against. Okay, I'll verify by mail. Well, until next week. If this is done, this will be moved to Tuesday of the following week. So that would mean there will be no test next week. That's the following week. But I'll verify with Moodle that it's okay with everyone. Okay, if there are hard exceptional cases, if somebody once has an exceptional case and cannot attend the test, we can always arrange a private organization of the test for exceptional cases. Good. Then let's dive into the heart of the topic. And we start today with methodology. Call it easy but important. Yes? The programming homeworks can be done in groups of 2. Yes. Same thing for the mini project. They can be done individually or in groups of 2. We start with methodology, which is the easy part. It's a lot of common sense that we could skip, but over the years I've noticed that perhaps it's still good to remind a number of things. So what is performance about? Here are two examples that you can find that I saw in practice in the past. Compare Windows versus Linux. So people did papers on that. Evaluate the power consumption of a telecom box. Assume one of you has to do this as a mini project. What would you do? Yes?
First of all, define precisely what you want to compare, because obviously Linux is not clear. The time to complete a task, or power consumption, or memory consumption, and then run a few different cases by varying different parameters one at a time.
Excellent. So first, what you want to measure, that's what we will call the metric. When you say Linux is what, as you said, computing time, for example. And also design experiments that might give different outcomes depending on what conditions we do, what program we compile, for example. That's what we call the factors of experiment. Another opinion? No, there isn't anything. Well, here's what those people did here. So this is a paper that you can find the references in the lecture notes. And they did a number of things, like here, for example, on the y-axis, they show the number of cycles that is done by a certain job that has a certain size, which consists in showing, I guess, with ghost view, which is not a very classic application, and for various versions of a Unix operating system, in that case NetBSD, and 2 versions of Windows. So here, what we see on the y-axis is what we can call the performance metric. You can measure, for example, if 2 machines have the same processor but just different operating system, how many CPU cycles does it take to do the same job with Linux and with Windows. And here we find that with Windows it takes more, which is what all studies have with this kind of standard jobs here. Here we find another graph that is showing number of events. So events are things like memory system calls, I guess, and memory read actions here. And here it's for different, what we call benchmark, different kind of jobs that are given here. No, sorry, this is not for different benchmarks. This is memory read reads generate reference. Okay, to an array. So this is a benchmark that was made by the people who did it. So we see here the concept of benchmark that we will use a bit later. And here what's important is to discuss is whether the things they are measuring are the correct one. Another example here is another paper that produces a formula of this type. Well, they say, here's my telecom box, here's the total energy consumption. You know, one of the hot topics now of telecom and internet hardware, you know, it's power consumption. Because when we go to 5G and to more and more power everywhere, we realize that the internet is consuming a large fraction of the energy in society. And they want to somehow reduce that. And here is what those people found. They said the total power consumption is 0.35 Pmax, where Pmax is some weights are the maximum power that this device can compute, and here is the power it computes when its utilization factor is 50%. What we find here is that the factor that we will probably always find in everything we do is the load. How much work does the job have to do? So of course, if your telecom equipment is doing a lot of work, you expect it to consume a bit more power. And a very good telecom equipment would be one that is proportional. So a very good power equipment would be one where the total power consumption is proportional to the load. Here we find something that's a bit different here. So to make this long story short, the first thing, as you had suggested, that we want to introduce when you will do your performance evaluation is what is your metric. The bad news is there is not one metric that is defined in the book and required. The metric is domain dependent. If you're analyzing a compression algorithm for big DNA databases, then the metric is the compression ratio. If you're analyzing the power consumption of a telecom equipment, the metric is the power consumed over the time. So the integral of power, the energy. So that domain, that requires some domain expertise and needs to be screened by somebody who knows the system, which in the mini project will be you. But normally it's just a matter of good sense, common sense, to find what are metrics that make sense and don't make sense. There are a few problems with metrics that we will discover and discuss in a special chapter about what I call the viewpoint. We'll go a bit through that in a few minutes about the Simpsons paradox, which is when we define a metric, we define what we're interested in: power, throughput, speed, etc. But also it has to do with how we measure it. When we say what is the speed of a program, what do we mean exactly? How do we measure it? We need, if we will do an experimental process or simulation, we need to define how we measure. And sometimes we will see the way we define the measurement can bias the metric. We'll come back to that. It's what we can call the sampling bias, or the importance of the viewpoint. An example of sampling bias is I take an arbitrary train ride. Is it late? Is it not late? What is an arbitrary train ride? Is it one where we take all the possible trains that exist in the timetable and we see how many were late? Or is it one that is obtained by asking people when they exit the Lausanne railway station, were you late today? The sampling is a bit different. Good sampling should correspond to what the metric of interest would be, what the experience done by users of the system will be. So that's part of the problem that we will see. Sometimes we're not able to do it. Sometimes we're able to compensate for the difference in viewpoint. If I come back to the train system, why is there a difference between the two viewpoints that I gave?
Data is the sample is considering only the people who come to the sample. Example is might be biased. There's some special.
Correct. So we do a local sampling instead of a uniform global sampling. That is a bias that is practically unavoidable. So we will never measure everything. But there is another one that's more vicious. If I take all the trains that are in the timetable, I include all the trains, even the small trains that go in the mountains of Jura and have 2 people on board, and that may or may never be late, and I put them in the same integral of things as the trains between Lausanne and Geneva that are full of people and that are always late. So if I ask a random person, many of the random people will come from a train where there's lots of people and not from a train where there's few people. So if I sample by train or by person, I will find a difference average. Sometimes it may be non-important, sometimes it may be significant. That's one of the things we will need to screen. Let me skip this one. Very often when we have metric, there's not one, but several. Here, we measure the performance of a web server, and we find this for configuration A. So this is just software, it's a different web server software. And here is the power consumption, the response time to benchmark of request, and the throughput, so transactions per second. Throughput is typically larger if response time is smaller, and vice versa, but it's not necessarily always exactly the same. What configuration do you prefer? So many people like A, that's the majority. So why is A better? Well, the power consumption is small, and the response time is also small, but not the smaller. So if I see here, D has a smaller response time, higher throughput, but consumes more. So then you say it depends. Well, that's the reality here. Here it depends. I cannot say that A is better than D because it depends what I want. Here I have a cheap thing that is energy conscious, but probably runs the processor at very economically. Here I have more throughput, so it depends what I want to optimize. So I cannot say that A or D is better. However, there are things I can say. For example, here I can say that if I compare D to B, right? D, if I compare this to that, right? B has a response time which is larger, a throughput which is smaller, and a power, and it consumes more power. So it's probably a Windows machine versus Linux, right? So it does the same job, it costs more, and it's slower. So there are still things we can say. We can say that B is dominated by A. So one of the key things to realize is that first, it will not very often be like that. You will not have one metric that you aggregate and you think this is the best. Some consumer organizations do that. They compare vacuum cleaners, they examine 5 different criteria, they weight them and they say, here is the best. But this is cheating, this is not scientific. You never know how to put the weights. Here it's the same. What is more important is the power. One thing we can do though is first learn how to display the things, and second, recognize that there is still a concept of there might be configurations that are better than others from all viewpoints. That's what we call they dominate. And then the question becomes, what are the non-dominated ones? The non-dominated ones are the only ones that are of interest. Because the ones that are dominated, there is always another one that performs better from all viewpoints. It's less expensive, it performs better, it has a longer lifetime. You always prefer. So here, one way is to do what is called a spider plot or a caveat diagram, where you put as many axes as you have dimensions. So it's not a geometric representation. There's only, you do it in a flat space. Here there are 3, but it works with 10, 20. And then you simply draw a line, and you will very quickly see what are the ones that are better. So I draw the line here such that higher is better. So I put the response time with negatives, and power consumption also with negative, because higher absolute value means worse. And then I see very clearly that there are 2 diagrams that intersect, so they're not dominated, but all the others are below. So that's one little trick to plot the result of something when you have typically many dimensions, which practically always you will have. 3 is not much here. We mentioned also the load. Well, let me skip that. The load is, for example, in the case when I want to do Linux versus Windows, we've discussed the metric. You also need to discuss the factors in general, and the load in the world of computer system is very important. The performance of a machine depends typically dramatically on its load. Some machines may be good at low load and bad at high load, or vice versa, or always bad, but that has an impact here. So here the load is typically, for example, the size of the job that we give here, and the metric is what we find here on the y-axis. So we find 2 important things we need to think when we have a project. What is our metric? What is the thing we want to measure that is meaningful? And what is the first factor, which is the load? Of course, you need also to know what's your goal. I mean, why are you doing this performance analysis? Is it in order to decide whether you will buy a Windows versus Linux PC? or so easy to do a comparison. Very often things are more complicated than that. You want to give, for example, guidelines about what to use under which circumstances, which is, for example, to what is called engineering rule. Engineering rule is trying to find a formula that at the end, like this one, gives the performance, predictive formula for the performance when we put some of the parameters as input to this formula. This is what we will want to do when the performance is not a final result, but depends on the configuration. If you have to do this versus that, the techniques will be different. If you need to do a comparison, then the load is very important. If you need to do an engineering rule, then the loads might be one of the inputs here. So here you need to be spending a lot of time making sure you analyze all the possible load cases. Here you may simply assume that you take it as one of your input variables and leave it to the users of your formula to see that. Okay. In practice, we will do that, of course, during this refinement period of the mini project. So let's move on. Now let's go into what I call patterns or traps that when you do your first performance evaluation or in general when you measure a thing in experimental sciences, things that are a bit unusual, and if you do it for the first time, you may be fooled by some things. Here is an example here. So the example is, so it's a real example. So people have studied the performance of a TCP implementation for mobile ad hoc devices, so devices that speak from smartphone to smartphone. And you expect, in principle, that when the things are very mobile, so one of these experiments was done by Aladdin Epfl, was a PhD student, and is now developing a flash sales application. So he tested the performance of this on bicycles running around the campus. Right? You can test it also in cars or in trains, or with pedestrians, and you expect that pedestrians should see a better performance than cars, because when you move very quickly, the configuration changes very fast. My device is talking to yours, that forwards it by propagation systems to another one, etc. But if we move very fast, many of the attempts may fail, for example, because we don't stay in contact long enough, or because the topology is always changing. So we expect the performance of the throughput performance of TCP decreases with speed. So this is what we did here. The speed is in meters per second. So this is from pedestrian to slow bicycle, if you want, here. And this is the throughput that we see for a number of experiments that is done. And each of those points is one value. So we had one example where the speed was that and the throughput was this. So we transferred the small images and saw how much time it takes and computed the throughput based on higher throughput is better. Then what people do usually when they have a diagram like this, they say, well, let's do a linear regression. We'll talk about that a bit later. So put a straight line here through this cloud of points using one of your favorite linear regression tools. And this is what I did here. Here is the line I found. Therefore, I conclude the throughput increases with the speed. This is what this measurement tells me. Not much, but still a bit. Things get a bit better with speed if I do this analysis. Of course, this is against expert intuition. Before doing this, you still have to do it to verify. Perhaps you have to quantify the degradation, and you find the opposite. So when you find something like this, you stop and you think. So what would you do at this stage if you are the experimentalist and you've done this? Majority of you said, no, it is not true. So which means you are not blindly following this, which is good. That's an illustration of what I call the scientific method that we will discuss again. One common mistake is to do the following thing. You do an experiment, or you get results from another experiment, and then you look at the data, you analyze the data, and you draw conclusion from that, and that's it. That's the kind of things you could do. Somebody who knows nothing of TCP and mobile mobility and etc. gets this data, will do the straight line, and will say it increases. It's scientifically proven. Right. What is wrong with that from a methodology viewpoint? Here I'm challenging you because you know, I mean, the result is obviously counterintuitive, so there must be something wrong. But if the result were not counterintuitive, the methodology would still be wrong. What is wrong is we have seen some data, then we draw a conclusion, but there are lots of explanations that could explain the data. You're just posing one. And scientifically, in physics, when we pose a hypothesis, we can think it's correct only if we've done a number of experiments trying to invalidate it. There must be a loop between seeing something, extracting from this a hypothesis, then you verify it. It's like in a thriller, right? You want to know who is the murderer. You've seen a knife there, or there's a knife in your pocket. You are the murderer, but still I want to investigate. Why is the knife here? Could you have put it there? Is your DNA on it, etc.? I still want to verify my hypothesis by checking all these implications of this hypothesis. So that's a very important thing to do whenever we draw conclusions. So we do an experiment. If the experiment is not made with all the care and all the reasons to validate or invalidate the conclusion, we have usually to do more. Until trying to break the conclusion, we are in a fixed point where we find no way of breaking it, then we can start believing in it. So here it would be too early. We would need to design other experiments. We can pose as a hypothesis that mobility increases throughput, and then we would need to design experiments to see. But here, in fact, we were fooled by aggregation and what we can call the hidden factor paradox. Here I'm showing, in fact, that there is a hidden factor, which is because all the devices were done in, experimental thing always takes a lot of time. It's like doing this camera to work. You try it once, you come the second week, what worked the previous week does not work anymore. So we did this experiment on a number of devices. Some of the devices were configured with a small socket buffer, some others with a large socket buffer. Why? Well, in principle, it should not happen, but it happened. Because they were not the same devices, or they had not been installed with the software at the same time. And in fact, the socket buffer size, when it's too small, is a bottleneck for the performance. So the TCP is waiting for things to happen simply because the socket buffer on the receiving side or on the sending side is full. So there is one factor that influences the performance, is the speed condition in which my mobile is. But there is another factor, which is, here we can call it a nuisance factor. It's an undesired factor that we'll do a break, but I'll finish on this slide here. There is another factor that also influences the performance, and that was hidden in the previous slide. Now I reveal it, I show it. By showing this is the graph we had before. Now I put a L, capital L, or a small case s for the large buffer size and for the small socket buffer size here. Now I have two clouds of points, the cloud of points with a large buffer size and the cloud of points with a small buffer size. And I do two linear regression for each of the two clouds. What we find is that for the large buffer size, the performance decreases, the throughput decreases. For the small buffer size, it remains practically the same. Therefore, the conclusion is reversed. We had before the impression it's increasing, but in fact it was increasing because there was a hidden factor that was probably as important as the factor of interest, and this hidden factor was not properly randomized. We had all the slow speed devices at small socket buffer size. It's stupid, but if you don't look for it, perhaps you will not know it. And the large buffer size are also only for the high-speed devices. So perhaps this experiment was done before by pedestrians, and then we went with a bicycle, and then we had to reboot the system or did something different. It looks stupid, but that's the reality of performance evaluation. When you do it, you're immediately confronted with that.